All right, welcome back. Let's talk about some partial derivatives. So this will be a new playlist that I'll be doing talking about partial derivatives and applications. Now, the first type of partial derivative is the first order partial derivative. But before we get into that, let's just talk about functions for a second here. So we can have a function of one variable like y equals f of x. And in this case, an example might be you have a ball and there's a height as a function of the horizontal distance, like a parabola, basically, in this case, in the ideal sense. But a function can be more than one variable. So here we could have multivariable functions, like z is a function of x and y, or perhaps w is a function of x, y, and z. Let's take the latter here. Example might be from economics. We have cost of production as a function of the number of units of goods x, y, and z sold. We will do examples that are very generic in this video. However, they do apply directly to ones that I've seen in the past talking with students. So let's get into these functions of one variable and the notation for a first derivative. The first derivative in Leibniz notation, dy dx, or with the function notation f prime of x, stuff that you would have seen in an earlier calculus experience. What about multivariable functions? So let's talk about the function z, which is a function of two variables, x and y. We can have our first order partials, which are di z di x. That's how you say it, di z di x, and di z by di y. We could use other notation because the function is called f. We could say di f di x or di f di y. Or if you really want to be compact, you could write subscripts, f sub x, f sub y. In this video, I'll tend to use the subscript notation saying fx, fy, or f sub x, f sub y. As you do them more and more, you're probably a little bit lazy like me and say them a little bit more compact. What about the three variable function or function of three variables w here? We could have first order derivatives with respect to each of the variables x, y, and z. So di w di x, di w di y, and di w di z, or we could use the function g, or we could put subscripts with g, or even w, wx, wy, wz. The thing that might be scaring you is that there's lots more variables, so perhaps partial derivatives are exponentially harder than the functions of single variable, but don't be scared, as I pointed out here. The idea here is that only one of the variables is active or changing when you're finding a partial derivative, and all the other variables are constants. So if you have like x, y, and z, and you're doing a partial derivative with respect to x, then the y and the z are fixed or constant. You can just pretend they're like numbers or constants like pi or e or whatever. I'll go through, I think, about 10 examples. As I do these videos in one take, I forgot how many examples there are, but I believe there's 10. So let's talk about some second derivatives, perhaps in a later video. Okay, let's go. In this first example, we have a function of x and y, which is a quadratic type function. If you plotted this in 3D, it's going to be a paraboloid, not a parabola, a paraboloid. You could probably throw this into Desmos or something and take a look, or Wolfram Alpha, or perhaps on your Mac, you can even do the 3D grapher. Okay, the partial derivative with respect to x. So now remember, x is the variable here. Y is not changing. And then di f di y is where y is the active variable and x is not changing. So let's talk about di f di x first. Go term by term. The derivative of x squared, yeah, it's 2x, just like it did in the past. No problem. But what about the second term? Well, it's going to be 0 because that second term does not depend on x. In other words, as x changes, that second term will be the same because the y value is frozen, if you like. In the second step here, we have the first derivative with respect to y of 0 for x squared because x squared that term does not contain a y. And then the derivative of y squared with respect to y is 2y. And we can quickly clean these up. So here we have just 2x and 2y. With functions where there's the variables are interchangeable in a sense, like I don't want to say an even odd nature specifically, but where the x and y's are interchangeable, there's corner shortcuts you can take, I guess. I like to do that when I'm checking my answers. but I like to do the derivatives independently just because you never know if you make a silly mistake. And in this situation, I'm writing down the first order partial derivatives with the compact notation, which I will use for subsequent steps in the video. In this next example, we have a function of two variables, no longer quadratic in nature, but we do have an interesting situation with the middle term where there's an xy product. So there will be some more complication here, but let's see if we can get our heads around it. The first derivative with respect to x and y, let's go. So term by term, the derivative of 4x squared, 8x. The second term has an x, but the 11y is constant. So really you're doing the derivative of x there, which is 1. So that's why the x disappears. And the last term does not possess an x. That's why I don't write anything down for it. And for the derivative with respect to y, there's the middle term, which is 11xy. The derivative of y there is going to be 1, so you have 11x left over. And then the derivative of 3y cubed is going to be 9y squared. That's pretty much it. Now, these ones here, I didn't do a lot of coloring and intermediate steps, but if you stick around for the rest of them, I do tend to take more detail as the questions become more complicated. Here's an example where we'll have a combination of an exponential function and a polynomial type function. So let's take a look and see what happens here. The derivative of the first term with respect to x, well, that x squared is only going to become 2x, and the 5y cubed is constant. So the stuff in yellow there is going to not change. That's why I'm just highlighting it as it is. And the derivative of e to the x is e to the x with respect to x. Now, what about f sub y? Well, that partial derivative is going to have only one term because there's only one term that contains a y in it. So that e to the x that you see right here, that e to the x does not relate to y, so it's not going to change. And then the derivative of y cubed is 3y squared, your basic power rule. And we can clean up some stuff here. So I'm just cleaning them up and without too much discussion. Hopefully you just pause the video there and clean it up on your own as well. Okay, let's take a look at the next one. Here we have a situation where the function is a rational type, and we have a function of x on the top, and the denominator depends on y. I want to write this two different ways, I should say. So we have this way as well, and then there's a third way as well. Now, each of these ways will serve as an advantage depending on what we're doing for partial derivatives. You could do quotient rule for all the rules here, but I want to save myself the writing and show you perhaps the most efficient way that I could solve it. So let's take a look at the first derivative with respect to x, the first partial derivative. So in this case, the second way that I've written the original question is beneficial because the fraction 1 over 5y squared plus 1 is not dependent on x. So just leave it as a constant. And then you have the derivative of 2x, which is 2. Then for the derivative with respect to y, it's beneficial to use the last notation. You don't have to, but this is, in my opinion, the most efficient way. And you see I've done it there in magenta color. We have a power of a function rule or a chain rule if you prefer. So we covered that in an earlier video. If you need any references to the older videos, let me know in the chat. I might put them in the description as the video library on derivatives becomes more complete and I can kind of reference them better. Let's clean these up a little bit and express your answers with positive exponents. Hopefully that wasn't too dangerous for you. These are the ones that tend to get people because they might be overwhelmed with which rule to use. In this next example, we have a famous looking form. For those of you taking economics, perhaps you're familiar with the Cobb Douglas model. Now, my training is not economics, it's engineering, but I have seen enough economics in my undergrad and postgraduate studies to know a little bit about the Cobb Douglas model. In this case, the key thing is that we have rational exponents on the variables x and y. There is a relationship in the formula, which I'm not going to get into economics here. Let's just see how we can do these derivatives and present them in a friendly way. The derivative of the first, with respect to the first variable x there, is just going to be a power rule. And with rational exponents, we'll clean that up after. And then with respect to y, we also have a rational exponent power rule. So you bring the 2/3 down. And then the exponent negative 1/3 appears because you do 2/3 minus 1. We can clean this up a little bit. So I've crossed out the 6 and the 3, or make that with positive exponents and a single exponent as well with brackets. Second derivative there at the bottom, I did 6 times 2/3, which is 4, and then cleaned up the exponents in a separate step with the brackets x over y. Okay, now we'll talk about some functions of more than 2 variables. So here we have a function of 3 variables, and I've also called it g. Not all functions are called f. Sometimes you have to use different names for different functions within the same problem. And when we do talk about multivariable optimization in this playlist, I intend on including that. We do need to have several multivariable functions depending on what constraints are involved. In this case, let's take a look at the first order partials with respect to x, y, and z. G sub x, g sub y, g sub z. So with respect to x, I've colored them for you there. So the derivative of x is 1, and then the yz are fixed, so they're just like constants or numbers. Sine of xy, we have the derivative of sine, and then the chain rule. Now the chain rule there, remember the derivative of xy right here, the derivative of xy with respect to x is going to be 1 and then y, so 1y. G sub y, a very similar pattern, except x and y you can see are interchangeable. So by a similar logic, we have a very, very similar result. G with respect to z, well, that first term has a similar pattern to the earlier terms, but then we don't have to worry about the trig function, just the power z to the 4, which is going to be 4z cubed. And we can clean those up and move on with our day. Okay, in this next example, we have a function of t, u, and v, and the name of the function here is w. Let's spice it up a bit. So we're going to see a power rule that is similar for all of the first order partials with respect to t, u, and v, because the outermost step is a power of a function, or a chain rule, if you like. So we have here our first partials, and there we have it. So you see that it's always going to be 3 bracket to the 2, and then inside we have a function of t, u, and v, but we only care about the t term because we're doing wt, w sub t. And the derivative of 5t squared is 10t with respect to t. And you'll see that for the second term, the beginning is identical, and then the chain step will be with respect to u, giving us a derivative of negative 11. And again, for w sub v, that first part with the bracket is the same as the previous two. And we have a chain step with the derivative of v with respect to v, which is 1. These can clean up a little bit, but nothing too dangerous that you can't handle. Okay, here's one that has a combination of a rational function and an exponential function. This function here, f, depends on 3 variables, x, y, and z, and it will be beneficial to write it a few different ways. So there's the original way, the OG way. Then we have our other 2 ways here. We have 2 separate terms, and we have this one here where we're writing z to the negative 1. Each of these forms can be used depending on what you prefer, but also your affinity for efficiency. So let's take a look here. F sub x, well, I've chosen the second version here because the second version, it has e to the x squared, and then 1 over z, which is constant. So you see the 1 over z out here is just a constant. So we can just put that aside and then use a chain rule for the exponential. The derivative of the exponent is 2x. The second version also is beneficial for the derivative, partial derivative with respect to y. Since 1 over z is a constant, similar to the previous one, we only have to take the derivative of y with respect to y. So that's a 1. And finally, f sub z, well, that last version is actually beneficial because the quantity in the bracket is essentially constant, and we're talking about changing with respect to z. Then we can apply a simple power rule, albeit with negative exponents, to find the first order partial with respect to z. A little bit of housekeeping here. And we have our first order partials. I think this question is probably one of the tougher ones, but I do believe you've already got through the worst of it. That one we did earlier, like the Cobb Douglas one looking, that's a good one too. Here's one that has similarity in terms of the x and the y. So whatever the first order partial was with respect to x, we would expect something similar for y. There's a very nice symmetry here. So the first thing I'll do is remind you that there is a rule we covered in an earlier video, and you can see it down here. The derivative with respect to root u, with respect to u, is going to be 1 over 2 root u. This is a pattern that I covered in an earlier video. So I apply that pattern immediately whenever I see a square root, because I don't feel like writing it to the half, and nor should you. You can pattern this out. Then we do a chain rule for the derivative of the radicand, that is the quantity in the radical, and that's just 2x. Because we're doing it with respect to x, we don't care about the y squared. Its derivative is 0 with respect to x. In a similar way, we can do the derivative with respect to y. Starts off the same way. We're working on an outer root or bracket, if you like. And then on the inside, with respect to y, we have y squared becomes a 2y. So you see this beautiful symmetry. I've also crossed out the 2's there if you missed that little step there. Okay, one last question here. Let's talk about an inverse trigonometric function. I recently made a video on derivatives, ordinary derivatives, first derivatives of trigonometric functions, including inverse tan or arctan. So let's an opportunity to try this one out. We have here the derivative of arctan of u, which is 1 over 1 plus u squared. That's a very famous one. I actually derived something similar for the arc sine in the earlier video as well. So we do the 1 over 1 plus that bracket quantity squared. Now, this step will be identical for f sub y, but then the chain step will be different here. Now, take a look here. This quantity here is going to be differentiated with respect to x, not y. So this x squared is going to become a 2x, but we don't care about the y. That y is just going to multiply it. See? 2x with a y, 2xy. And we can clean that up later. There's that opening step again with the arctan. Now we differentiate this with respect to y. So this term here, that y, the derivative becomes a 1. And then the x squared, it's just constant. So it's x squared times 1, or x squared. And there you have it. Simplified nicely. Hopefully nothing too threatening. I hope that your partial derivatives experience has improved. There's lots of calculators on the internet called partial derivative calculator. You can Google it, or you can throw one in the chat if you're stuck on it. Hope you have a lovely day. Talk to you later.